Hello. Let me know when you can see and hear me, please. Hi, happy Friday. Hello. Hi, hi. Hi. Who do we have? Hi, Kimia. Hello. Who else is there? Is it me and you? Hey, why not? Anyone that is over on TikTok, reminder that I'm only going to be able to see messages and comments, etc., on YouTube. So if you want to actually talk about this topic, then go to the link in the bio and then you'll be able to join the YouTube live stream. Okay, but hi to everyone on TikTok. Come over to YouTube if you want to get the full experience. Hi, Timo. How are you? Let's get started. We have to stick to, we're on a strict half an hour today, and we're going to do kind of like the basics, the starting of the rate equation. I've got, as usual, a few questions planned, but if you have any particular questions on the rate equation that you really want me to talk about, then please let me know. Okay. Otherwise, we're just going to look at a couple of the basics of the rate equation, which we see in year 13. Usually. Okay. Hi, A. Hi, capital A. Okay. So when it comes to the rate equation, the standard, I was going to say standard form, but that means something. The general form is rate is equal to K, which is our rate constant, multiplied by the concentration of one of our reactant or catalysts raised to its power, and then multiplied by the concentration of another reactant or catalyst raised to its power. Okay. Now, again, A and B, they don't just have to be reactants. They can be reactants or catalysts, because we know catalysts affect the rate of reaction, so they could also play a part in the rate equation because they'll give our alternative pathway with a lower activation energy, blah, blah, blah. Okay, when it comes to the order, that is the power to which the concentration of a species is raised in the rate equation. Now, typically, and for A level, we only really need to consider zero order, first order. So not order one, but first order and second order. Does anyone know what the relationships are between rate and concentration for each of these orders? Anyone want to share? Are there any year 13s here? That's a really good question. Oh, wait, Kimmy is definitely year 13. Do we want to stick with rate equation? Because we can always just go to a general ask me anything if this isn't a topic that we really actually want to focus on today. Okay, I've got lots of blank slides ready for any questions that you have. You haven't learned this yet? Anyone want to stick with rate equation? Anyone want to ask me anything instead? I'll take a vote. Majority wins. Stick with rate equation or ask me anything. ... Anyone? Anyone? Hello, hello, hello. Okay, completely new. Okay, you're doing it after Christmas. Okay, lovely. Let's talk about it then, because I think it will be a nice head start. So when we say zero order, what we mean by that is that the rate is directly proportional to the concentration of our particular species. I'm going to call this A, raised to the power of 0. And we know that anything with our math skills, anything raised to the power of 0 is what? Anything raised to the power of 0 is what? Lovely, A, 1. So essentially what that's telling us is if a substance is zero order with respect to if the rate is zero order with respect to the concentration of one of our reactants or catalysts, it means that the rate is independent. Can I spell? One day. Is independent of the concentration. I haven't given myself enough space. I'm just going to write conc. Okay. So zero order means the rate is not going to depend on the concentration at all. For first order, that means that rate is proportional to our concentration of our species. I'm just going to call that A to the power of 1. which again, mathematically speaking, means that the rate is directly proportional to the concentration. Okay, so if the concentration is multiplied by 3, then the rate will also be multiplied by 3. If the concentration is multiplied by 100, the rate will also be multiplied by 100. Okay, and then we can probably guess where we're going with this. For second order, rate is proportional to the concentration of our species raised to the power 2, so squared. So that is telling us that rate is proportional to the concentration of A squared. So if the rate were to be multiplied by, if the concentration of A were to be multiplied by 2, what would happen to the rate? Oh, that's a good question, but answer mine first. If the concentration were to be multiplied by 2, what would happen to the rate? Lovely. Thank you, Kimia. The rate would be multiplied by 4. So whatever the concentration is multiplied by, the rate will go up by the square of that. Okay? Absolutely. 2 squared. So let's put that into practice with a couple of questions. Again, even if you haven't seen this before, hopefully you'll start to pick it up and then you can show off when you do it after the holidays or when you do finally see it. Okay? So, actually, no, before we get to those examples, it's really, really important to note that the rate equation, so figuring out all of these orders, does not come from the balance symbol equation. So it's not like Kc and Kp, where the concentrations are just raised to the power in the equation. We can only get the rate equation from experimental data. Okay, so by doing some practicals and figuring out how the concentration of a particular species is affecting the rate. Okay, we won't necessarily have time to talk about those practicals today because, again, this topic will cover, like 10 hours of lessons. But again, any particular questions that you've got on this topic, please, please, please ask me in the chat. If you're on TikTok, come over to YouTube if you want to ask me in the chat. Link is in the bio. Okay, so let's say I'll say a student has carried out an experiment and it showed that the rate of this reaction up here at the top is directly proportional to the concentration of methanol, the concentration of H plus, and the concentration of Cl minus. If we wanted to write the rate equation, all we're doing is removing the proportionality by including the rate constant, lowercase k. So rate is equal to k, lowercase k, because uppercase k is an equilibrium constant, lowercase k is our rate constant, multiplied by our concentrations of each raised to the power of 1, which we don't need to write. Oh, I've just answered that question. What are the orders of reaction with respect to methanol, H plus, and Cl minus? What would you call those orders if they're raised to the power of 1? Anyone? Hello, hello? Thank you, A. Lovely. We would call that first order or first order. Absolutely. Okay. Now, to determine the units for the rate constant, now this is where it does become similar to like Kc and Kp, where the units are going to change depending on the orders within the rate equation. Because our units for rate, our standard units for rate will be moles per decimeter cubed per second, right? Change in concentration per unit time. So change in our concentration in moles per dm cubed per second. That's our rate. Then that's going to be equal to K multiplied by our 3 concentrations. Now, each of these concentrations is measured in moles per decimeter cubed. So if we just substitute in the concentrations, that's K multiplied multiplied. Oh my goodness. Multiplied. Moles per dm cubed. So in order to find the units for K, we just, thank you, A, we just rearrange. So we will say that K is equal to, I actually kind of like it. I think I'm going to start saying multiplied it. I think it's my new favorite thing. K is equal to moles per decimeter cubed per second divided by moles per decimeter cubed. Then, if anyone gets to the final units before me, let me know. Then we cancel out anything top and bottom that we can. So we can get rid of our moles per dm cubed on the top completely. And we can get rid of one of our moles per dm cubed on the bottom. Oh my gosh. Wait, how did you get 113%? Timo, how is that possible? Mathematically, we end up with seconds to the -1 on the top, and then moles squared decimeters to the -6 on the bottom. But we want that all as just one line, right? One set of units. And anything that's on the bottom, we just flip the sign and bring it up to the top. So our final units will be moles to the -2, decimeters to the +6, seconds to the -1. Okay, sometimes you'll see the decimeters cubed and the moles written the other way round. So if you see it written as dm to the 6 moles to the -2 seconds to the -1, I mean, same thing. How do we know it's first order? By looking at what they told us. Well, they told us twice. Okay, they told us that the rate of reaction is directly proportional to each of these three species. Okay, so that's already telling us first order just in words. Now, if we didn't pick that up from the question, they've now told us in the rate equation, rate is proportional to the concentration of methanol to the power of 1, because the 1 is invisible, concentration of H plus to the power 1, because the 1 is invisible, concentration of Cl minus to the power 1. Why do we do to the power 3? Because there's 3 of them. 1 plus 1 plus 1 will give us 3 overall. Okay, lovely, Miss Val. We are indeed sticking with rate, don't worry. Okay, so we're combining all of our concentration terms so that we can figure out the units. And these will be our final units for the rate equation, so for K. Okay, lovely. Next question. Next question. Okay, any questions? Keep them coming. What do I recommend prioritizing for Christmas? Oh, that's a really good question. For Christmas, I think it depends on a couple of things. If your mocks are after Christmas, then prioritize everything, right? Do some past papers. So do like a whole past paper, and then identify from those papers which topics you're struggling the most with, and then do some really focused revision on those particular topics. Okay, year 12 is a great one to go over, especially if you haven't gone over it recently. So going over year 12, but don't forget to also consolidate the trickier year 13 bits, because it's really easy. It can be easy to go, okay, I'm doing this currently, I'm getting it, so I don't really need to go over it, but then it doesn't get cemented. Okay, so make sure, yes, year 12, but don't forget to do some light practice of the year 13 stuff to keep it fresh in your mind, and make sure that doesn't go too far back in your memory that you can't find it anymore. Okay? Okay. But again, your best bet, whichever topic, whichever area you decide to focus on, application is key, okay? Do not just open your textbook and go, oh yeah, great, that makes sense, and then close the textbook again. If you haven't done some past paper questions, if you haven't marked them as harshly as you possibly could mark them, then you haven't practiced, you haven't revised. Okay, so application, marking as harshly as you can, and then review whatever you're still struggling with. Okay, lovely. So Let's bring our rate equation to some actual data. So nitrogen monoxide reacting with hydrogen. Sure, great, lovely. First, we want to state and explain the order of reaction with respect to each reactant. So in order to do this, remember, we must not just look at the balance symbol equation and go, oh, it must be second order for NO and second order for hydrogen. It does not work like that. We have to use the experimental data. So what we'll do is we'll look at our concentrations of each species and how they're changing, and then how that affects the rate of reaction. So if we start with our NO, we want to find 2 experiments, so out of our 3, where the concentration of NO is changing, but the concentration of H2 is staying the same. That way we can see what is the effect of NO on the rate. Which experiments, therefore, will we choose? Which 2 experiments can we compare to find the order with respect to NO? Anyone? Any takers? Absolutely, star platinum. I mean, you're living up to your name, 2 and 3, because our concentration of NO is changing, but our concentration of H2 is staying the same. So our concentration of NO has been multiplied by 3. Our rate, what's happened to the rate? What's that gone up by? Oh, quick maths. I mean, maybe we can tell already. I can tell. I'm not trying to show off, but we've only got a couple of options, really. What has our rate changed by? From 24 to 216. Not by 3, that would only be 72. Multiplied by, absolutely, star platinum, by 9. Absolutely, great, Nanima. Hi, Batman fan. Hello. Hi, Lara. This is year 13, so you're welcome to stay, but this is going to be way in the future for you. So we can see that when our concentration of NO was multiplied by 3, the rate, or the initial rate, really, more specifically, was multiplied by 9, which is 3 squared. Therefore, the order with respect to our concentration of NO, what order must it be? If when our concentration went up by 3, lovely, star platinum, order with respect to NO is second order. Wonderful. Let's do the same thing. Great. Well done. Let's do the same thing for H2. Let's find 2 experiments where the concentration of H2 is changing, but the concentration of NO is not. Which ones will we look at? Oh, what's going on there? Thank you, Misbah. Absolutely. Great, Dave. 1 and 2. So our concentration of H2 has been multiplied by 2. What's happened to our initial rate? Oops, initial rate, lovely, times 2. Therefore, wonderful, excellent. The order with respect to the concentration of H2 is first order. Great, they are directly proportional. Lovely. I haven't given myself any space to write the rest of this answer. Wow, I just got so overexcited. That's fine. We'll do that's part A done. Part B, write the really rate equation for the reaction. Oh, Sienna, of course. Sienna, I remember you. Oh, I'm glad that you are here. And I hope you're following on TikTok, LaJoy Does Chemistry, because there's so many videos there now for A-level. And LaJoy does GCSE chemistry for any GCSE students that are here. Although, why are you on your phone at school? Is that allowed? I don't know. Let me not comment. So to write the rate equation, that's going to be rate is equal to our lovely Sienna rate constant. and then multiplied by the concentrations of our species raised to their power. So for lovely star platinums, that will be the concentration of NO squared, because it's second order, multiplied by the concentration of H2 to the power of 1. So the 1 is invisible. Yeah. Okay. Oh, so we have a couple of collabs, right? I've got my collab with Laura for biology, collab with all three of us. I have a collab with Brooke coming soon-ish, and then yeah, we'll do some more. I think they're really fun. So those are all on the Miss Tucker Does Chemistry or on Instagram as well. Yeah. Okay, lovely. Part B is done. Part C, calculate a value for the rate constant. How can we do that? How can we calculate a value for the rate constant? Any suggestions? It's actually really straightforward. So, oh, absolutely. So we're going to just rearrange, lovely Kimia, to make K the subject. So K is equal to, remember, lowercase k, rate divided by the concentration of NO squared multiplied by the concentration of H2. And then, Dave, you are absolutely right. We can choose any of our three experiments and just substitute the values in. Okay, it doesn't matter which one we choose, our answer will come out exactly the same, regardless of whether we choose experiment 1, experiment 2, or experiment 3. I'm going to choose experiment 1 just because it's the first one and the numbers look quite nice. So 12 divided by concentration of NO squared, so 0.01 squared, multiplied by the concentration of H2, just to the power of 1, we end up with, okay, yay, amazing stuff, Platinum, love to hear it. Okay, anyone with their calculators that can do this quicker than me? I'm looking at you, Batman fan, if you're still there. My year 12s always put me to shame with how quick they are with their calculations. It's actually really embarrassing at this point. Oh gosh. Did you get 1.2 million? That feels ridiculous. But hey, what are you going to do? Yeah, Kimia, the next one has got slightly trickier numbers. I'm going to do 1.2 times 10 to the 1, 2, 3, 4, 5, 6. Why do I pronounce 0? Oh, I say naught. Naught. Naught means naught means 0. Like noughts and crosses, right? Noughts and crosses? Naught. Yeah. And it's quicker. It's quicker than saying 0, especially when there's lots of zeros, right? To say 0.0000, like you just sound ridiculous to me. Well, I sound ridiculous. Let me not speak for you. Okay, so I just say 0.000. For some reason, that sounds less ridiculous to me. I don't know. Okay. O, yeah, O works too, but then O, I'm just thinking of oxygen. So as a chemist, I'd rather not. Okay. For the units, we won't work them out again. This is overall third order, right? We've got 2 plus 1. So our units are going to be the same as the last one we just figured out. Moles to the -2, dm6, seconds to the -1. Okay. Oh, in the interest of time, I'm going to save part D for a lesson on rate determining step and mechanisms rather than trying to teach it in the next 7 minutes. Okay, so we're going to do the next example where the numbers are a little bit trickier. So where we don't always have two experiments where all of the numbers are the same. Okay, so let's go. But any questions, as usual, let me know. So here we've got 3 species, hydrogen peroxide, iodide, H+ ions. We've got 5 different experiments. We want to find the order with respect to each. So our first thought, hopefully, would be to find 2 experiments where the concentration for one of them is changing, but the concentrations for the other 2 are not. So if we start with the hydrogen peroxide, quite nicely, we can see experiments 1 and 2, the concentrations of I- and H+ are staying the same. So we can just use these two. Our concentration is multiplied by 2. What's happened to our rate? What's happened to our rate? Lovely. Thank you, Star Platinum. Also times 2. So must be first order with respect to H2O2. Lovely. For our iodide, again, let's find 2 experiments where the concentrations of our peroxide and our H+ are staying the same, but our concentration of iodide is changing. Can anyone spot which 2 experiments would we want to look at? Which 2 experiments? Lovely. 3 and 4, absolutely. So our concentration has been multiplied by 2. What has happened to our rate, our initial rate? Be careful with the powers. Anyone? Oh, do I know? Yeah, I do. Hello? Are you still there? Hi. Hello? What's happened to our rate? Remember, we've only really got a couple of options, right? So we can kind of narrow it down. Our rate has either multiplied by 2 if it's first order, multiplied by 2 squared, so 4 if it's second order, or it stayed exactly the same and multiplied by 1 if it's 0 order. Which one is it? Wait, have you all left? What's happening? Is the chat not working? Absolutely. Time. Oh, wait, no. I take it not times 4. If you put, let's get rid of the standard form for now. Let's just try and figure out between 5.25, yeah, Kimia, absolutely, multiplied by 2. Okay, because 5.25 multiplied by 2 gives us 10.5. Okay, so multiplying by 2, I'm just going to get rid of this here. Multiplying by 2, if we just ignore the powers for now, would give us 10.5. But 10.5 times 10 to the minus 6 in standard form, that's 1.05 times 10 to the minus 5. Okay, so if we go up by a unit of magnitude, is that what it's called? I think so. Then, is that what it's called? I can't, oh my gosh, my brain is going crazy. Okay, then we need to make sure that we look at our powers accordingly. Okay, so also first order with respect to iodide. Let's do our last one in our last 2 minutes. Oh, I think we'll get there. Okay, now to find the order with respect to H+, unfortunately, we do not have 2 experiments where the concentrations of the other 2 species are staying the same. But it doesn't matter because we already know the orders with respect to the other 2, so we can use what we've already figured out to find out the one that we are missing. Okay, so what I would do first, the way I would approach this is I want to know the order with respect to H+, but I'm actually not going to look at the H+ with the rate just yet. I'm going to start just by looking at the H2O2, the one that I already know. Okay, the concentration of H2O2 has been divided by 3. Okay, now because I've already figured out, I say because we have already figured out that this is first order with respect to H2O2, what would we expect to happen to our, what would we expect to happen to our rate? What would we expect to happen based on the order that we figured out? If the concentration of H2O2 was divided by 3, we would expect that the rate does what? First order, directly proportional. If the concentration is divided by 3, then the rate, thank you, Star Platinum, will also be divided by 3. So we would expect, and we'll just plug it into our calculators, that if only H2O2 was having an effect, our rate would be 1.05 times 10 to the minus 5 divided by 3, which is 3.50 times 10 to the minus 6. Now we can see, based on this new initial rate, what the H plus is doing. Okay, because we've already taken into account what the H2O2 did, now we can look at what the H plus is doing. Okay, now the concentration of H plus is being multiplied by 2. What is happening to this new imaginary rate and the actual initial rate? What's been the effect? What's been the effect of the H plus concentration? Lovely, no effect, multiplied by 1. Therefore, it must be 0 order with respect to H plus. Okay, because this change is only because of the H2O2, not because of the H plus. Okay, very last thing before we have to go, because, oh gosh, I'm going to be late. The overall order for the reaction, we just add together the individual orders. So first order plus 0 order gives us overall second order as the overall order. Okay, you're very welcome, Star Platinum. I hope that you all found this useful. Next week, I think we're going to redox next week. So I look forward to seeing you then for the times. Make sure that you are, watching either Instagram or TikToks so that you know exactly when it's going to be, or that you're subscribed to my newsletter and it will be in there as well. Okay. Okay. Well, hi, Sabiha. Yeah, I do this. Great. Lovely. I'll see you. Well, if you're in my year 13 class, I'll see you in a few hours for our lesson. And everyone else, I'll see you next week. Okay. Bye, bye, bye. Bye, everyone. Bye, bye.